So our next speaker is Dr. George Sowers. George has 30 years of experience in the space transportation field, during a continuous span working for Martin Marietta, Lockheed Martin, and United Launch Alliance, including a stint as Chief Systems Engineering for Atlas V development. Sowers helped develop more than a dozen launch systems. He recently retired from his position as Vice President, Chief Scientist at ULA, where his team developed an architecture for fully reusable in-space stages, fueled by propellant mined, refined, and distributed in space. He has a bachelor's degree in physics from Georgia Tech and a PhD in physics from the University of Colorado. And George is a fellow with the American Institute of Aeronautics and Astronautics. George.
Thanks, Rand. Appreciate the introduction. Before I dive in, I'd like to just take a second and plug the Space Resources graduate program at the Colorado School of Mines. Back in 2018, we rolled out the world's first, and it's still the only graduate program in space resources. It's fully online, so you can be enrolled from anywhere around the world. We currently have students from 5 continents, and I think we're up to 23 different countries. It's a multidisciplinary program. You can get certificates, masters, and PhDs. And some of the other panelists on this on this webinar are actually students in the program. So I'm going to talk about lunar ice mining, propellant production, and distribution. And I appreciate John Mankins for teasing this presentation a little bit. So one of the great discoveries of planetary science in the last several decades is that water is ubiquitous in the inner solar system. It's at the poles of Mercury. We know it's abundant on Mars. It's contained in hydrated minerals in near-Earth asteroids, and it's also at the poles of the moon. And the fact that water is so abundant is very, very fortunate for human exploration of the solar system. It's essential for life. It contains oxygen for breathing air, and it makes a great radiation shielding. But what I'm going to be talking about is splitting water into oxygen and hydrogen, then liquefying them into liquid oxygen, liquid hydrogen propellants, or using water directly as propellant with either steam propulsion or plasma propulsion or other means. And I've been saying this for a few years now. Water is the oil of space, and hence it's going to be one of the cornerstones of the space economy. So water on the moon exists in permanently shadowed regions, PSRs, near the poles of the moon. The low obliquity of the moon results in constant grazing sunlight. So you have these regions at the poles, crater bottoms essentially, that never see sunlight. They act as cold traps. So if you've ever had volatiles on the moon that migrate their way into these locations, they get frozen and stuck for billions of years. The existence of water at the lunar poles is confirmed by many remote sensing data sets. You can see neutron spectrometer data on the chart on the right. It was directly confirmed back in 2009 when we crashed a Centaur, one of my Centaur upper stages, into the Cabeus crater with a direct measurement of 5.6% ice by weight. And then here's a pretty famous picture of surface ice indications of up to 30% ice from a paper by Shui Li back in 2018. Now, unfortunately, all of these data sets are subject to interpretation. Before you can really economically extract ice and turn it into a business, we must characterize it as what's known in the industry as a proven reserve. This requires detailed knowledge of the extent, the richness, the distribution, and the geotechnical properties. You need to know what the ice is like and how much is there so you can design systems to extract and process it, and also develop business cases in markets. This is going to require ground truth. We have to get prospecting vehicles down into these deep, permanently shadowed regions. One of the challenges down there is going to be power. You have no sunlight since it's permanently shadowed. These two pictures show a concept that we developed under a NASA grant with a student-led team last year, with a laser power beaming station that you would put on a crater rim in the sunlight that would receive power and transmit it to a receiver on a rover in the permanently shadowed region that would then be doing detailed mapping. But it's imperative that we get that detailed knowledge before we can really determine if we have a business case for ice. So John talked about this a little bit. I've worked on a concept that uses reflected sunlight to heat the surface of the moon. We've shown through some proof of concept testing at the School of Mines that that's actually effective. If there's not enough ice on the surface or in the near subsurface, there are other methods that are passive, like implanted conducting rods that would conduct heat into the subsurface and allow vapor to escape to the surface. That actually enhances sublimation rates substantially. We've done some proof of concept testing at Colorado Mines that shows that this actually works. Using a lamp to simulate the sun and preparing icy regolith simulants that we then placed into a cryogenically cooled vacuum chamber at School of Mines. We showed that surface ice is absolutely rapidly sublimated by this, and we can actually penetrate the subsurface to a certain extent. How far into the subsurface is right now TBD and is limited by the size of the samples that we've been able to test. One thing I'm excited about is that I've been able to find some money to start up some more testing along these lines later in the summer. So ice extraction is just one part of a bigger architecture that is part of a propellant production system. I did a lot of work on this architecture as part of a NIAC grant a year or two ago. These colored boxes show the various architecture elements. Ice extraction over here in green. There's a number of different rovers. There's the water to propellant processing system. So once you have water, you need to purify it, electrolyze it into hydrogen and oxygen, and then liquefy it into propellants. Then there are a number of other systems. The good news here is that NASA is actually investing some early technology money into some of these elements. And I'll just highlight down here in orange, with the water to propellant processing system, Paragon Space Development Corp has a contract with NASA to look at both purification and electrolysis. Colorado Mines is supporting Oxeon on a tipping point contract to look at solid oxide electrolysis. This is using the same technology that's currently creating oxygen on Mars with the MOXIE experiment. And then Blue Origin has a tipping point award that's looking at the liquefaction side of it. Okay, so that's all on the supply side. There were some questions in the chat already about markets. I've spent a lot of time thinking about propellant markets. Back when I was at ULA, I actually made a public offer to buy propellant in space, and stimulated at least a little bit of interest. I'm very confident that propellant markets will exist once we have a supply, because it all comes down to the rocket equation. And what the chart shows is without refueling, you had this horrible exponential increase in propellant mass required to go a certain delta V. You can see the benefit of one refueling or two or three. So that exponential increase, which we know is the tyranny of the rocket equation, becomes linearized. So refueling is truly a game changer. And anything we do beyond low Earth orbit, every single mission or activity benefits from refueling, whether it's civil or military or commercial, international, every single mission will benefit. And I see an eventual transition to a completely refuelable water-based ecosystem for transportation in space, whether it's using water directly in terms of steam or plasma, or for high thrust and high ISP applications or high thrust applications using LOX and hydrogen. One prerequisite for this is that we need a refuelable transportation architecture. Again, the good news here is that every single rocket company that I know of is currently studying and planning to incorporate refueling, whether it's SpaceX or Blue Origin or my former employer, United Launch Alliance. And NASA recently has invested several $100 million in demonstrations for transferring in space cryogenic propellants. So the cost model that I've been using for the last 4 or 5 years is shown on this chart. If you're trying to bring everything from Earth, that tyranny of the rocket equation is reflected in these blue bars, where the costs rise exponentially the farther away from Earth that you get. On the other hand, if you can source propellant on the moon, these green bars, you can get substantial reductions in costs. And the orange bars represent the cost reduction you get by refueling launching from Earth. So just to give you an example, the numbers I've been using for the cost to land to launch mass to the surface of the moon, $35,000 a kilogram, can be cut by a factor of more than 3 if you refuel one time on the way from Earth to the moon. So it's an enormous lever. I put together some demand estimates. We're talking total aggregate demand for propellant, and this is all normalized to what it would be on the lunar surface, of almost 3,000 tons per year. So this is quite a bit higher than the 50 tons that John Makins was talking about. Most of the demand is not on the lunar surface. It's refueling upper stages on their way from Earth to GEO, or Earth to an interplanetary destination, or Earth to the lunar gateway, or propellant to fuel a Mars mission. And then I've also been in discussions with the Space Force about the potential of a strategic propellant reserve in space. So I won't go into this in detail. I just recently published a paper in the journal New Space that gives a lot of detail on business cases. The important point here is that if we stick to commercial only, you can get positive returns, but the numbers are less than 10%. I'm a strong proponent of a COTS-like public-private partnership model, where NASA can be both an investor and a customer for propellants. There's a huge benefit to NASA from doing this. And in that case, a private entity could get north of 15% return on investment. So I think there's a business case there, and that's based on the demand that I showed previously. All right, so one of the important points is that the propellant that we're producing on the moon, most of it is not used on the lunar surface. A little bit is. There's a little bit of demand to refuel landers so that we can get back off the moon to somewhere else. A lot of the demand occurs from refueling upper stages on their way uphill from Earth, or refueling satellites in geosynchronous orbit, or in providing propellant for potential Mars missions. And so this chart kind of shows you a distribution network where you've got on the lunar surface, you've got water mining, propellant refining, you've got water and or propellant tankers that are moving that propellant from the lunar surface up to a depot at EML1. You've got tankers that are moving propellant to a Mars mission aggregation point, notionally EML2. You've got, in the future, water mining from near-Earth asteroids that are bringing it into an aggregation point at EML1. EML1 is a great location for that sort of a distribution node because it has access to essentially every Earth orbit. So it can meet the upper stages on their way uphill. It has very low delta V to access geosynchronous orbit, and you can get from the lunar surface to EML1 with pretty low delta V compared to what it takes to get from Earth. So the final piece of the puzzle is this EML1 logistics node. This is some work that we recently did under a grant from the US Air Force. I did in conjunction with a company called Lunar Outpost. But basically what it shows is essentially a propellant depot located at EML1. You've got cryogenic fuel storage tanks that, in my mind, are spent upper stages. They're repurposed upper stages that turn into propellant storage tanks. They're located behind a sun shield. And work we did at ULA shows that you can get hydrogen boil off down to less than 10% per year through purely passive means. One of those means is a sunshade. So this thing's always pointed, that sunshade's always pointed at the sun. Those cryogenic storage tanks are always in the shadow. They're also spun. So that whole right-hand side of the depot spins at a low rate to keep the propellant settled, which also enables you to reduce the boil off and aids in transfer. There's also water storage at the other end of this thing. And then in the middle, you have, electrolysis module and a fuel cell module that allows you to take water, convert it to hydrogen and oxygen. And if you need extra energy for some reason, for some other application, then you can run it back through a fuel cell and turn the hydrogen and oxygen back into water. But this node is that central piece of architecture that then now results in a overall cislunar propellant economy fueled from propellant mined on the Earth and eventually on asteroids.
Great, George.